generic form of a polynomial up here on the board. I said previously a polynomial was going to be a sum of constants and power functions, and that's what this amounts to. If we say n is a whole number, now that just means it's either a positive integer or 0, okay? Then we can say a polynomial function is going to look like so. Now, these numbers a with a subscript, these are just my coefficients, okay, or my constant term, okay? And the subscript just tells me a sub n, that's the coefficient for the nth power of x. So a sub 5 would be the coefficient for x to the 5th, okay? So it just gives me a generic way of writing that. Notice a sub 0 would just be a constant, but notice if I had something like f of x equals 2, that's the same as 2 copies of x to the 0, because x to the 0 power is just 1. So I can almost think of this as the coefficient in front of x to the 0, although we usually just call it the constant term. So here, I would have this would be my constant, and assuming that n is 1 or more, these guys would be my power functions. Now, we are going to require that a sub n is not 0. The other ones can be, but right here, I've got that n is the biggest power of x that I'm writing, okay? I can't write 0 copies of that. So for example, if I had something like f of x equals 4x cubed minus 2x, there, my a sub 3 would be 4. So I've got 4 copies of x cubed. My a2 would be 0, because I don't have any x squareds. My a1 would be negative 2. Notice the sign is considered part of that coefficient. And my a0, my constant term, would be 0. So it's totally fine to have 0 as a coefficient or a constant term some of the time, but we require that the coefficient in front of the biggest power that we write not be 0. That's because we're going to define that biggest power to be the degree of the polynomial. So the degree is the biggest power of x that occurs with non-zero coefficient. So this would be degree 3. I could say I've got 0 copies of x to the 4th, but that doesn't make it degree 4, because in order to count towards the degree, you have to have a non-zero coefficient. Okay. Notice that means if I do have a constant polynomial, the biggest power of x that occurs would actually really just be 0. Let's just take a look at that. If I have something like f of x equals 2, that's a constant, but that counts as a polynomial. So that would be 2x to the 0. That has degree 0. And that's going to be true for any non-zero constant. Okay, I can view it as that many copies of x to the 0. If I have the 0 polynomial, so if f of x equals 0, we call that the 0 polynomial. It is a polynomial. It's a constant function. It's also a polynomial, because all constant functions are polynomial. For this one, we're going to say the degree is undefined, because it really kind of looks like that coefficient is 0, but we're not supposed to have 0. Now, so that's the one polynomial that won't have a defined degree. That's not going to be a big issue for us, but it is important to know that for non-zero polynomials, the degree is just the biggest power of x that occurs with a non-zero coefficient, and that means that if I have a constant polynomial other than the 0 polynomial, it's going to be degree 0. Okay. All right. Now, I've written this polynomial in what we call descending order. So I started with the biggest power of x, and I worked my way down. That's a really convenient way to write things, and I'm usually going to choose to write things in that format, but it's not necessary. So if I had f of x equals 5x cubed minus 2x squared plus x minus 3, that's a beautiful third-degree polynomial written in descending order. But that's exactly the same as if I wrote x minus 3 plus 5x cubed minus 2x squared. This is the same polynomial. I've just rearranged the terms so it's not in descending order anymore. Okay. So it's not necessary, but it will often be helpful to write things in descending order. We define the lead term of a polynomial to be the largest, let's say it this way. The term whose degree is the degree of the polynomial. So it's going to be the term with the biggest power of x. So it's 5x cubed. We call that the lead term. If you write things in descending order, the lead term will be the first one you wrote. If you write things in a different order, the lead term is not the first one you wrote. The lead term doesn't change. The lead term is the term with the biggest power of x, so that the degree of this term matches the degree of the overall polynomial. Okay. Now, in the first section of this chapter, we were looking at quadratic functions. So if I have a quadratic function, that was something like f of x equals ax squared plus bx plus c, where we specified that a was not 0, so that we actually had some x squareds. Well, that just means it's a polynomial, and the degree would be 2. Okay. So, using the notation that we're using now, I might have written that as a2x squared plus a1x plus a naught. It's much more convenient when you've just got 3 of them to call them a, b, and c. Okay. The subscripts are particularly useful when you're writing sort of a generic one and you don't know what n is. When I do know what n is, in this case it's 3, I just use the first letters of the alphabet. Okay. But the quadratic functions that we were looking at earlier are examples of polynomial functions. All right, what I want to talk about now is the end behavior of a polynomial. So let's just say I have f of x equals negative 2x cubed plus 4x squared minus 2x plus 5. So I've got this third degree polynomial. Okay, and I want to describe the end behavior. So I want to say as x goes to infinity, f of x goes where? I want to try to fill in that blank. And I want to describe the end behavior on the left side of the graph. As x goes off to negative infinity, f of x is going to go where? So we're trying to fill in these two blanks. Now, in the past 2 videos, we looked at how to figure out where power functions went. So if I just go term by term, I can see what happens. Let's talk about infinity first. Okay. As we go off to infinity, x cubed goes off to infinity. Okay. Multiplying it by negative 2, this piece is going to go to negative infinity. I'm just going to use an arrow to indicate that that's where that piece goes. Okay. If I look at the next term, x squared would go off to infinity. Multiplying it by a positive number, that doesn't change, so this is going to go off to infinity. Looking at this term, x would be going off to infinity. Multiplying it by negative 2, that negative is part of the coefficient, this piece is going to be going to negative infinity. And 5 isn't going anywhere, it's just busy being 5. Okay. Now, you'll notice I just used this arrow notation. I did not write negative infinity plus infinity, minus infinity, plus 5. That is a big mathematical no-no, because arithmetic is defined for numbers. I cannot do arithmetic with infinity. And the problem is, it looks like negative infinity and infinity are opposites of each other, so that they should just cancel each other out, because that's what happens with numbers. But that's not what happens with infinity. As we go off to infinity, all of these first three terms are big. These guys are big and negative. This guy is big and positive. Okay. They're all big, but that doesn't make them the same size. If you remember, when we were graphing our functions, let's just take a look at odd power functions. There's y equals x to the first, and here's y equals x cubed. Now, as we go off to infinity, as x goes off to infinity, both of those y values go off to infinity. But that doesn't mean they're the same. The green graph, the y cubed, is way bigger than the blue graph, just the x. This is going to get much, much bigger. So they're both getting infinitely big, but because they're getting big at different rates, for any fixed x value, the bigger power is going to be a lot bigger. Okay. We can take a look at that if we just look at some big powers. Let's say that x was 1 million. Now, I think of that as a big number. That's because I have a very finite mind and I can't really comprehend super, super huge things. But in the scope of the world's population or the national debt, that's actually a very small number, okay? But for my small mind, I think of that as a big number. Okay. Now, if I look at x squared, that would be 1 million squared. What that's going to do is that's going to just double the number of zeros. So 1 million has 6 zeros. 1 million squared is going to have 12 zeros. Now, if I look at x cubed, that's going to triple the number of zeros. So that's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 zeros. That is way bigger than x, even though I started with x being 1 million, which made me think of it being a big number. So what's going to happen is that even though 3 of my 4 terms are big, the one with the biggest power is way bigger than the others. So what we can say is that as x goes to infinity, or as x goes to negative infinity, polynomials are dominated by their lead terms. So in this case, the lead term was this negative 2x cubed. So as x goes off to infinity, f of x is going to go off to negative infinity, because we had indicated that was what was happening for each of these terms. Okay. All right, if I were to look at as x goes to negative infinity, let's just see. My lead term was negative 2x cubed. I'm just going to look at that off to the side here. If we're going off to negative infinity, x cubed would be going to negative infinity. We're multiplying by a negative, that's going to reverse that, so f of x would go off to positive infinity. Oh dear, this was not supposed to be an equal sign. That was supposed to be an arrow. I apologize. We can never equal positive or negative infinity. We can only approach positive or negative infinity. All right, I'm going to just sort of illustrate why this happens with this particular function, looking at what happens as x goes off to infinity. It's like we're having a tug of war, and this piece says, I think we should go to negative infinity. So that piece is trying to take us in that direction. This piece here says, no, I disagree. I think we should be going off to positive infinity. This piece says, I agree with the big guy. I think we should go to negative infinity. And then this piece says, oh, please, couldn't we just stay here at 5? It's so lovely here at 5. Let's stay here. Now, if you imagine that this is a tug of war, so I'm going to attach a rope to all of these guys, okay? And now, these two are trying to move us this way. This one is trying to move us this way, and this one is just trying to stand there and stay put. Who's going to win? Whoever's got this guy on their team, okay? So, because this is so much bigger than all of the others, even though these guys might be big, they become negligible when you compare them to how big this one is. And that's only true as x goes off to infinity and negative infinity. But for end behavior, polynomials will be dominated by their lead terms. So in the next video, we'll practice describing the end behavior for a number of polynomials.